Before refrigeration, ice cream was a handmade luxury. Ingredients went into a mixing bowl, inside a tub filled with ice and salt water. The salt helped the ice absorb heat, cooling the mixture to below freezing. In the 1920s, commercial freezers made mass production possible, and the ice cream industry was born. To make ice cream treats, you first have to make the ice cream. It all begins with fresh cream. The factory stores it in refrigerated silos set just a few degrees above freezing. The silos feed a high-speed mixer that blends the cream with other ingredients. The main dry ingredients are powdered skim milk and plant-based stabilizers and emulsifiers. Stabilizers prevent the ice cream from crystallizing, and emulsifiers allow the mix to bond with air during the whipping process. The other ingredients are sugar and corn syrup. After about 3 minutes of mixing, a pumping system moves the mixture into pasteurization tanks and heats it to 162 degrees for half an hour, killing any bacteria and activating the stabilizers. Then, the factory homogenizes the mixture, a process that breaks up the fat globules, giving the ice cream a smooth texture. The mixture is cooled and concentrated vanilla flavoring is added. Then, the concoction is chilled and whipped for about 15 seconds. Whipping blends the mix with air, transforming it from a liquid to a soft solid. Without air, the finished product would come out looking like frozen milk rather than ice cream. The ice cream sandwich wafers are made of chocolate cake ingredients. A filling machine feeds 2 lines of wafers toward an injection pipe. Just as 2 wafers come together, the machine injects 1/3 of a cup of vanilla ice cream in between. The pipe's head shapes the ice cream into a rectangular slab that fits perfectly between the wafers. All this happens at a rate of 140 ice cream sandwiches per minute. As the sandwiches move on to packaging, the filling is still ice cold from the freezing phase, so there's no threat of a meltdown. The packaging system raises each sandwich into a wrapper, then folds and tucks the ends. The next machine counts the sandwiches and inserts them into boxes. Once sealed, the boxes go directly into a storage freezer at -22 degrees. On another line, ice cream cone production is underway. A feeder drops pre-wrapped sugar cones into holders on a conveyor belt. Sprayers coat the insides with a chocolatey layer, which adds flavor and creates a barrier between the cone and ice cream, so the cone remains crispy until you eat it. Next, nozzles squirt in the ice cream filling. 1 production line, 2 flavors. 1 row of cones gets vanilla ice cream, the other row, chocolate. Now for a tasty surprise in the cone's core, an injection of liquid caramel. This factory also makes ice cream cones with chocolate and strawberry sauce inside. Next, a chocolate-flavored liquid topping. Then, the crunchy finishing touch, a layer of chocolatey-coated puffed rice. Finally, the cones move under a lid dispenser that applies a wax-coated paper lid to each one. A heating element instantly melts the wax, sealing the lid to the cone's paper sleeve. From here, the ice cream cones go into boxes, then straight into the freezer, ready to take a licking.
Until the mid-19th century, Mother Nature was the only producer of ice, and the idea of man-made ice seemed preposterous. It was a Florida doctor who, in need of ice to cool feverish patients, invented the ice machine. The technology took a few years to refine, and then they were ready to chill. Today's commercial ice makers churn out ice on demand, allowing restaurants and other businesses to keep things cool at all times. To make one, machinery folds the edges of stainless steel sheets so they can be assembled into the ice maker frame and exterior panels. Meanwhile, copper uncoils over a roller, which removes the curl from the metal. A machine spiked with blades then punches the copper. In one action, it cuts numerous slits in the strip and slices it to the correct length. The notched strips are now ready to be assembled into a grid. This grid is part of the evaporator. It's here that liquid refrigerant will evaporate, as it pulls heat from the water to freeze it into ice cubes. This copper tubing is central to that process. An automated arm bends it into a configuration called the serpentine, producing a coil that will fit on the back of the evaporator. As liquid refrigerant moves through it, it will draw heat out of the water. This machine flattens the tubing, giving it greater surface contact with the evaporator to facilitate heat transfer. Then it's into a big washing machine to remove any oils or oxides on the parts. A worker now applies strips of tin silver solder to the evaporator's backplate. This acid solution will act as a bonding agent. He then places the evaporator, solder side down, on the serpentine tubing and locks the assembled parts in an iron rig. He hoists the rig into an oven to melt the solder strips between the backplate and tubing, fusing the parts together. Then it's into an ultrasonic bath, where high-frequency sound waves clean off lingering contaminants. An inspector now examines the evaporator to confirm that the parts have been solidly fused. Next, he installs pipes on an ice maker side panel. These are the lines that supply refrigerant to the machine. He turns the assembly around and removes the caps on the compressor to connect it to a network of pipes. The compressor will force refrigerant through these pipes in a continuous cycle of heating and cooling to eventually produce ice. He brazes the joints to seal the connections. He attaches a fan to another side panel. It will blow cool air onto the radiator to cool the refrigerant and help convert it back into a liquid. Now he pumps the refrigerant into the system and measures the flow to ensure it receives a precise amount. Meanwhile, at another station, they assemble the ice bin. It's time to test this ice maker. Water flows continuously over the surface of the evaporator grid as the temperature inside the cells drops below freezing. Impurities like minerals are washed away as the water turns to ice, and the result is crystal clear cubes. Almost 6.5 pounds in just 15 minutes. Finally, they install the front panel on the unit. This job is done, and it's time for a little liquid refreshment on ice, of course. The sport of javelin throw dates back to the Olympics in ancient Greece. The athlete sprints down a runway and just before reaching a line on the ground, hurls the javelin forward. For the throw to count, the athlete can't step over the line, and the javelin has to land point first in the ground. This modern javelin consists of a long hollow tube and a point. The tube portion is called the shaft. This company uses strong, lightweight aluminum, but javelin shafts can also be made of steel or carbon fiber. The tube is 1.2 inches in diameter. It first goes into a taper machine where forming dies narrow the back end to very specific dimensions. The taper profile varies by model, but has to conform to international rules. After making the exact end of the taper, they slice off the excess tubing. The shaft is now its final length, 7.2 feet for a woman's model and 8.5 feet for a men's. A straightening machine sandwiches the shaft between two hydraulic cylinders. They apply extreme pressure, straightening any large bends. This is just a preliminary straightening. The final one comes later. Next, working strictly by eye, a specially trained technician sands the shaft, fine-tuning it to a very precise diameter and weight. The javelin's point section is made of steel tubing that's a hair wider than the shaft. After tapering the front, they saw off the excess, making the point around 12 inches long. Now for the point steel tip that jabs into the ground. They position it in a holder, place the point body behind it, then weld the two parts together. To make the point more aerodynamic, they sand down the weld line until it's flush with the surrounding steel. Using progressively finer grits of sandpaper, they polish away any imperfections until the point is perfectly smooth. Now for the final assembly. The shaft is sporting 2 coats of paint, and the point is nickel-plated to rust-proof the steel. They mark how far up the shaft the point will go and slip it on temporarily. As the javelin pivots precisely where international rules dictate, they add pieces of lead until the javelin balances. Then all the components go on a scale to ensure their combined weight abides by international rules. 1.3 pounds for a woman's javelin, 1.8 pounds for a men's. Next, they squirt a little glue inside the point and drop the chunk of lead inside. They drop in some knotted cord and ram it in with a metal rod. This packs in the lead so it won't rattle around. They use glue to adhere the point to the shaft. They drive home the point, so to speak, by throwing the javelin against a lead slab. The force of impact pushes the point into its final position. Now they recheck the javelin's overall weight. If it's underweight, they simply tape some sheet lead to the center of gravity, where the hand grip will hide it. Using a gauge to measure the grip's permissible length, they mark the grip position at the center of gravity, then mount the javelin on a lathe and coat the marked area in glue. They wind cotton cord around the shaft over the glue. Before cutting the end, they verify the length of the grip with the gauge. They apply 2 decals, one bearing the company name, the other a safety warning. But no seal of approval just yet. The javelin still has to undergo a final straightening. This takes an expert eye and a small hand-operated press to straighten out any bends. It's all a question of aerodynamics. The straighter the javelin, the more likely it is to go the distance.
Compressor blades are key components in a jet's engine. Thousands of them whirl inside the engine, rotating 400 times per second and whipping air into small hurricanes. Large compressor blades made of titanium compress the air in front of an engine's turbo chamber. In the back of the chamber, smaller blades made of nickel alloy compress it even more. The air heats up to more than 1,000 degrees, then combines with jet fuel, creating a powerful mix that explodes out the back of the engine. The blades start off as metal pellets called slugs. A ceramic layer prevents their surfaces from oxidizing when exposed to intense heat. The slugs are heated for 15 minutes in an 1,800-degree oven. Meanwhile, a robot sprays lubricant on 2 dies inside a press. The robot retrieves the slugs and loads them in the first die. The press applies over 1,000 tons of pressure to preform the metal. The robot then transfers the slugs to the second die, where they take the initial shape of the blade. The blades are dipped in water to cool. Another robot cleans the metal burrs off the edges. The blade is now an airfoil. Robots will shape the rounded base of the blade, called the dovetail, later. The airfoil has gone from this to this. After a new ceramic layer is applied, the blade is heated again. Each heating and cooling cycle tempers the metal, making it more resilient. Almost 1,800 tons of pressure gives the airfoil its final shape. A trimmer shaves off the excess metal. The searing heat has turned the protective ceramic layer into glass. That will come off later. It's taken an hour to shape the blade's airfoil. The dovetail, that nub on the right, is next. But first, this measuring machine inspects the airfoil. If any measurement is off by just half the thickness of a human hair, the blade doesn't make the cut. This casting machine will encase the airfoil in a matrix, a coating that protects the airfoil during work on the dovetail. The matrix is molded from liquid tin and bismuth. It solidifies into a metal cast around the airfoil. The future dovetail sticks out at the end. The cast is then loaded into what is called a broach machine. Its series of teeth carve the dovetail into its final shape. Now the cast can come off. A worker loads it onto the removal machine, and a hydraulic cylinder hits the cast at its weakest point, breaking it in half. The finished airfoil emerges unscathed. A dot matrix machine punches identification numbers onto the blade. Next, the blades are submerged in a fluid that penetrates any flaws in the metal. This inspection is critical, because even the tiniest nick can spell disaster when a jet's engines are working at full speed. Inspectors examine the blades under a black light. This one's perfect, but spots of fluorescence on this one indicate microscopic cracks and weaknesses. This one gets rejected. The dovetail gets 2 strips of rubber silicone that ensure an airtight seal when the dovetail slides into the slot on the compressor drum. A final check, and the blades are now ready for takeoff.
Your canoe may well be made of the same material they use to make bulletproof vests. That's right. Many canoes today are made of woven aramid fibers, better known by the trade name Kevlar. For canoes, though, they use a lesser density, since presumably no one will be shooting at you. A Kevlar canoe weighs about half as much as a wooden or aluminum canoe, and it's virtually maintenance-free. They build these canoes from several layers of Kevlar fabric, glued together to create a solid laminate material. It all begins with the fiberglass mold of the canoe's hull. The first step is to spread resin over its interior. Once that's done, they spread a sheet of Kevlar over the resin and rub it against the mold to push out any air bubbles. Then they trim off the excess fabric. Using a squeegee, they force out any excess resin and stretch the fabric until it's taut. This step ensures the laminate will turn out strong and smooth. They repeat this entire process with the second layer of Kevlar. Then run a roller over everything to expel any excess resin and press the layers tightly together. Now for some structural components. Pieces of thin, high-density foam go along the bottom of the hull. Glue bonds them to each other and to the bottom of the hull. Using a machine called a hotbox, they begin heating strips of foam to curve them. These curved pieces are called ribs. They reinforce the sides, adhering with resin. With the structural core of the canoe complete, they now encase it in a third layer of Kevlar. Once that's down, they prepare to bond everything together with vacuum pressure. They lay down a sheet of white fabric impregnated with a non-stick coating to prevent the vacuum bag from sticking to the surface. This mesh, called scrim, goes on next. It helps stimulate airflow during that vacuum process. Now they tape a plastic vacuum bag around the mold, sealing everything inside. Then they connect one end of a hose to the bag and the other end to a vacuum machine. The vacuum steadily draws out the air from within the bag, pulling the layers of Kevlar tightly together. After 8 to 10 hours under vacuum, the bag comes off. If a canoe flips over, flotation tanks in the corners keep it afloat. Workers build each tank out of 2 pieces of low-density foam. After sanding them to the right shape, they lay a sheet of fiberglass mat over them and coat it with resin. This strengthens the foam and seals the 2 pieces into one unit. After the resin cures for an hour, they extract the canoe from the mold. The factory's quality control inspector checks it over, and if everything's okay, applies a protective coat of resin. Once that's dry, they cap the edges with aluminum strips called gunnels, which keep the hull from folding inward. Then an aluminum crossbeam and a nylon end cap on each end. A wooden yoke for carrying the canoe upside down on land, and a wooden seat with nylon webbing. Workers rivet all these components to the gunnels, then rivet the gunnels securely to the Kevlar laminate. This factory puts every canoe it produces on a digital scale to ensure it meets weight specifications. If all is well, the finishing touch is a decal displaying the manufacturer's name. Kevlar canoes, like those made of other materials, vary in size, shape, and design. A canoe intended for fishing or hunting, for example, is quite different than one designed for long expeditions, or for a 2-person racing team, or for a solo canoeist.